Hello, everyone. Welcome back to another discussion in dynamics. Today we will Today we will continue our kinematics of rigid bodies. Okay, and we will focus on instantaneous center of rotation. Here. If you look at our timeline, you can see that we are in the kinematics part of our semester. And what are the subtopics? So far, we covered following subtopics. So rotation about fixed axis. It was a video you're supposed to watch on last Wednesday. Then on Friday, I showed you how to run velocity analysis. And today we will do instantaneous center of rotation. Okay. So plan for today is following. We will do brief lecture review, and then we will just do example number 1 and example number 2. Without further ado, let's dive straight into our discussion. Unless there are questions already. Let's do brief lecture review. Okay, so I'm going to refer to instantaneous center of rotation as ICR. However, I think Professor Sunny refers to it as IC. Okay, so it's either going to be ICR or IC. Okay, so let's assume that we have a rigid body here. Okay, and we know velocities of 2 points on that rigid body. Point A with velocity VA. Okay, and point B with velocity VB. So how to find instantaneous center of rotation of that body? I do usually that. I just draw perpendicular lines to these two vectors. So I just do this line and this line. Okay, these are 90 degrees. This is 90 degrees in here and in here. And I see instantaneous center of rotation is on their intersection here. That's it. Easy? Easy. However, now let's find omega body. So in order to find omega body, actually, you know what? I'm gonna put it here. Sorry. Let's find omega body. So if we would like to find omega body, we can go for such expression that VA is equal to omega body times this distance. This distance. Times this distance. Let's call that distance D. Okay, and since we know VA and D, we can find our omega body as function of VA divided by D. Okay, or we can also go for this distance. Let's call it L. And this expression is also valid. VB is equal to omega body times L. That's it when it comes to brief lecture review. Any questions? No questions? All right. So let's do example number 1. Please familiarize yourself with the problem statement before we start our solution. Or if you are watching this video on YouTube, just feel free to pause the video and read the problem statements and understand it. Okay, so what do we have in here? we have three bodies, right? We have bar AB, bar BC, and our color C, right? Our color is constrained, yes? Our color can go only along this incline, yes? It cannot leave that bar. Okay, so we know all the geometry of the system. We know that omega of bar BC is 20 radians per second, and they ask us to find omega AB. So let's maybe put already this omega AB on the picture. Let's assume positive direction. This is omega AB. By positive direction, I of course mean counterclockwise. So they ask us to find this value, plus they ask us to find velocity C. So velocity of this point. Okay. And now a little bit twist of the plot for today's discussion. Because topic of today is what? IC, yeah? Instantaneous center of rotation. However, I decided to solve this problem using velocity analysis first, and then we will solve it once again using IC approach. Is that fine with you? Yeah, I have my reason for that. Okay, so on this board, I will show you velocity analysis approach, as you can see on the top of your screen. Yes, here, velocity analysis. Okay, so how I would solve that problem? I would just start with velocity analysis between, let's say, points A and B. Solution. Velocity analysis between B and A, B with respect to A. So our velocity B is equal to velocity A plus omega of certain body times R B with respect to A. Okay, do you want me to ask you what certain body that is? Omega of which body is that? No, that's too easy. It must be bar AB. It must be bar AB. Yes, why? Because points A and B belong to that bar. Points A and B belong to that bar. Okay, so I'm going to write in here omega AB. Okay, what else do we know? We know that VA is 0 vector. A is fixed. I hope you can all see that A is fixed. If you look at the top right corner of your screen, you will see that A is fixed. Okay, that simplifies our problem. So our VB is equal to 0, 0 omega AB. Just recall that we assumed positive direction times this vector, RBA. I must draw it first on the picture, yeah? So I believe that RBA will be this red vector. This is our RBA. I hope that you all see that the components of RBA are 0, minus L, 0. Do you see that? 0, minus L, 0. Okay, let's do our determinant. IJK, 0, 0, omega AB, 0, minus L, 0. So this will be omega AB L, and the rest should be 0. Yes, 0, 0. Okay, we are done with our velocity analysis between points B and A. We cannot squeeze anything more. So now let's do our velocity analysis, velo analysis between C and B. So I can write VC is equal to VB, plus plus omega of certain body times r CB. And that certain body is obviously the other bar, yes? That certain body must be this bar, BC, because points B and C belong to that bar. Okay, so let's do it. So VC is equal to thing that we just found, so it will be omega AB 0, 0 plus this vector. I think that they gave us. I forgot how much it was. Can I scroll up the board? Sorry, yeah. 20, yeah? 20 counterclockwise. Aha, and now this vector. Let's draw that vector on the picture as well. RCB. It's also gonna be red. It's here. This one is RCB. And I don't even want to ask you for these components because it's too easy, yeah? It's L00, yeah? I just usually ask you those questions just to see if you follow what I'm doing, yeah? It's not that they're like very, I know that there are some simple questions, yes? L00. And also to like wake you up a little bit, you know? Yeah. Okay, determinant of this, it would be IJK. Pardon, sorry for that. Now we can work, yes? It's better. 0, 0, 20, L00. So this will be 0 here, 20L here, and 0 there. Okay, so our VC is equal to omega AB L 20L 0. Okay, so far so good? Everybody, any questions to what happened on the board? Okay. So, in here we have VCX and VCY and 0, right? But I think we can tell something more about this vector, VC. Okay, let me scroll up the board. Do you see, guys, that our point C can only move along this constraint? Sorry. Yeah, this constraint. You all see that, yeah? Okay, so is that true if I write that VC vector is equal to VC times cosine theta, sine theta 0? Would that be true? Yeah, clearly our vector, our VC must be pointing this way. Oh, sorry, I'll use black one to do that. VC must be pointing this way. Yeah, anyway, it must be pointing along that incline. Yes, so I think that this is true. Any objections? Yeah. Thank you, Madeline. That was a nice reaction. Yeah, okay, so we can actually write VC cosine theta, VC sine theta 0 is equal to omega AB L 20L 0. Okay, so we have two equations and two unknowns, right? Because we have expression for the x component and expression for the y component. So we can write VC cosine theta is equal to omega ABL, and VC sine theta is equal to 20L. Okay, and our unknowns are here. This is our unknown. VC is not known, and omega AB is not known. Okay, so I think that our VC can be found from here. So our VC is equal to 20 times 2.5 divided by sine 45 degrees. So our VC will be basically 50 square root of 2 radians per feet per second. And once we have a VC, we can plug it. We can plug it here, yes, and we can obtain that our omega AB is equal to VC cosine theta divided by L. So that would be 50 square root of 2 cosine 45 degrees divided by 2.5. And our omega AB will be 20 radians per second, which is a positive value. Okay, now vector-wise, our omega AB will be 20k radians per second, or if you prefer vector notation, you can write 0,020 radians per second. This is positive, yes, so it will be counterclockwise. And our VC is 50 square root of 2 cosine 45 degrees sine 45 degrees 0. If you grab your calculators, you will obtain that our VC is equal to 50, 50, 0 feet per second. And this is the end of the problem. Questions? Any questions? Okay, so that's that when it comes to velocity analysis of that problem. Okay, as you can see, there is a recipe in here. Yes, we just follow exact steps. Yes, we just write a couple of times velocity analysis between certain pair of points. Yes, it's very good for in computer era. Yes, so I usually go for velocity analysis when it comes to when I know that I have to use my computer, because I can just come up with equations and I can program my computer to do all the calculations for me. Yes, and then I can just go and enjoy my life. Yes, and my computer will work for me. So yeah, this approach is very good in computer era. And what's the topic of today? Instantaneous center of rotation. Yes, this is more pen and paper approach. Okay, let me show you why. I call it geometric approach. So now let us solve exactly the same problem using a different way. Sounds good? Okay. So please familiarize yourself with the problem. I'm kidding. No, don't. It's exactly the same problem. Okay. It's exactly the same problem. Okay. So our goal right now will be to find. Wait a second. To find VC using IC approach. Okay, so let's find IC of bar BC. Okay, this is our goal. So do you remember that recipe from the lecture review we did like 20 minutes ago? So we must find 2 points and 2 velocity vectors, yes, that belong on bar BC. Okay, so first of all, point C has no other choice, yes? That velocity vector must be aligned with this constraint, right? Okay, how about point B? Anybody want to help me? So how velocity B will look like? Yeah. Yeah. Thomas. Horizontal. It must be pointing either this way or the other way. Yeah. We don't know. Anyway, we don't care. Yeah, we just know that it must be horizontal.
You just know that from the last problem, or is there something? You just know that from the vector analysis of.
No, not really. But Thomas, do you want to say why we know that it will be horizontal? Yeah. It's pendulum. So exactly, yeah. At this instant, exactly, yes. So Trevor, if you look at the board, please. Yeah, look. So this bar is a pendulum, yes. So the trajectory of point B is actually this circle. Do you see? And this is L. This is, of course, radius is L. Do you see that? Yeah. So that's why Thomas knows that at that instant, velocity will be horizontal. Cool? We good? Okay. So what was the next step of our recipe? Let's draw two perpendicular lines to these green lines. Yeah. So these black lines here. Oh, sorry. Why you are not listening to me today? I'm talking to my tablet. Yeah. Yeah. Okay. I know how to do that. I don't do that. Okay. So this is horizontal line. Yes. Sorry, perpendicular line. And this is another perpendicular line. Okay, that was tough to draw, but okay. Okay, so it seems like they intersect at point A. Okay, so A is our IC of bar BC. Okay, so now let's find VC. So once we know where our IC is, now let's find VC. Okay, so VC will be omega bar BC times some distance. Some distance, yes? I think this distance. Can you guys tell me how much is this distance? Yes. So that would be square root 2L, exactly. Square root 2L. So this is equal, omega BC was 20, I believe it was 20. 20 times square root of 2 times 2.5. This is equal to 50 square root of 2 feet per second. Exactly what we obtained on the previous board. Yeah, look at your notes. It's exactly the same value. Vector-wise, VC, based on the picture, of course, VC will be equal to 50 square root of 2 cosine 45 sine 45 0, which is 50 50 0 feet per second. Yeah, based on the picture. Yeah. So exactly what we obtained previously. Yeah. Okay. Any questions?
The first
Oh, sure. Because of what we covered here. So this is true if D is distance between IC and that point.
Yeah. I just
Yeah, no worries. Yeah. Also, Professor Sunny, watch the beginning of yesterday's lecture. Professor Sunny spent like 5 minutes on actually explaining that. Yeah. Yeah. Or I mean, you see why that is true. Yeah.
Yeah.
Okay. Anyway. Any other question? Yeah. Dudów? Stuff? Yeah.
see, we just draw the line.
So this is the fastest way. Yeah. There is also a mathematical approach. You can do it. It will be more complex and it will involve more mathematics. Yes. This is called geometric approach, as you can see. Yes. We use the picture. Yeah. It is possible. Yes. Yeah. Okay. Any other question? Trevor?
When we're crossing the length with the should we be looking at the vector from A to C or from C to A?
The distance. So this is a scalar. Okay, so this is not a vector equation. Do you see any vectors here?
But should it be a vector equation so that we can have the direction of these things?
Yes, based on the based on the picture, I know that. Look, so this is what I know based on the picture. You can put it in your notes. Based on the picture. So I know that this is correct. So this is 50, 50, 0, and not minus 50, minus 50, 0. This is your question, yes? Why do I know that this is 50, 50, 0, and why is it not minus 50, minus 50, 0, yes? Because I can equally flip that vector, yes? Based on this counterclockwise rotation. Do you see that omega rotates the body this way, this way? So that point is going to now go this way, okay? It's not going to go this way. Can you imagine that? Yeah, okay. So that's why I said based on the picture. If you do not want to spend time on figuring out what, based on the pictures, things are there, use the previous approach, use velocity analysis approach. Then you don't have to think much because you will obtain your solution in a vector form. Yeah. We good? What does that mean?
I don't know. It seems like it makes more sense to do.
I agree with you, actually. Yeah. I just want to show you two, and you will choose which one you prefer. Fourth question. I don't have time to squeeze any fourth question. Okay. If you still have a question, I will stay after the discussion. Okay. So now, I would like to show you this example. So this example we solved on Friday, yes? We solved it using vector analysis approach, yes? Oh, Trevor. So this one was solved in the video on Friday, yes? So now we're gonna do it exactly the same problem, but using instantaneous center of rotation approach. You will decide which one you prefer better, okay? So spend a couple of seconds on familiarizing yourself with the problem statement before we start our solution. Okay, so even though we had that problem on Friday, I will just spend 20 seconds on explaining what we have in here. So we have three bodies, okay? We have three bodies. We have bar AB, we have bar BD, and we also have this body, this color D. And that color is constrained. Yes, it can only move back and forth along the horizontal line. What else do we know? Aha, we know that AB has omega AB. We also know the entire geometry, yes? Yes. We know the geometry, and they ask us to find velocity of this point D, this vector, VD. It is not known. Okay, in the previous video, you've seen velocity analysis approach, yes? Today, we're gonna do geometric approach. So how I would like to tackle it? Aha, I would like to find IC of beam BD. So let's start with finding, let's find IC of bar BD. Okay, we're gonna follow the recipe. So we need to find 2 points and 2 velocity vectors, yes, attached to these points. So I'm gonna go for the easy one, okay? I'm gonna go for point D, because clearly point D must move along this line. Yes. So I'm just gonna draw this horizontal line here. If I am able to do it. Okay. So for sure, our IC, our instantaneous center of rotation of beam BD will lay somewhere on that line. Okay. So anybody wanna help me? How to find another line? AJ. Yeah.
Being the path is a circle, so its velocity will be tangent to the circle.
Yes.
It'll be along the
Not BD. It will be along AB.
Yeah, the
Yeah, AB. Yeah, exactly. I hear you. Yeah. So this is what AJ said. So AJ said that our bar AB just circles around. Yeah. It just yeah. So velocity of point B will be perpendicular to that bar. So this is VB. Exactly. And this is 90 degrees. Okay, so next line, to find next line, I just must extend AB. Yeah, I must extend AB. Here. Yeah. Oh. What's going on? Okay. So okay, I managed to do it. So this is 90 degrees. Yes, and our IC is here. Perfect. Yeah. Thank you for help, guys. All right. So now, what they asked us. So okay, it's in the picture. So we done with this question. Yes. So now they ask us to find VD. Yes. So I think that our VD will be equal to omega BD times this distance. Let's call it H. So, or actually, you know what? Let's maybe draw this vector first. Let's introduce some vectors. So that vector will be R D with respect to IC. Okay, and let's say that our RD IC magnitude is equal to H. Can we do that? Yeah. So this is true. However, we don't know H and we don't know omega BD. Okay? But then let's also maybe find VB, because this will be omega BD times this distance. Let's say orange distance. Why not? Orange vector. So this vector is RBIC. And let's say that our magnitude of RBIC is maybe small d. Okay? So that would be d. Okay, but still we don't know what is omega BD and we don't know what is d. We must figure that out. And the rest of the discussion will be spent on figuring out what are those distances. Okay? It's clearly a geometric approach. Okay? So what I would like to start with is finding these two distances right now. I would like to find this distance and this distance. Let's call this distance x1 and let's call this distance x2. Okay? So I believe that based on this blue blue triangle. I hope you can all see that. Based on this blue triangle, I can write that our x1 is equal to L1 cosine theta. I believe so, yeah. And theta is 40 degrees, by the way. And L1 was 3 inches. So if you grab your calculator, you will obtain that this distance is approximately 2.298. Okay, now x2. Based on this blue triangle, we know that x2 is equal to L2 cosine psi. Yeah, I don't know. So do you remember that on the video on Friday, I introduced here psi? Yeah, I personally don't know how that letter is called, but for the purpose of this video, it's psi. Okay, I'm gonna call it psi. I don't know. I think it is psi actually. Yeah. So psi. On Friday, we found that psi was approximately 13 point. 13 point. I see it. 13.9482 degrees. Okay. So if you grab your calculators, you will obtain that x2 is approximately 7.764 inches. Okay, now we know that x1 plus x2 will be approximately 10.062 inches. Great. So far, so good. Any questions? Yeah. Beta. Okay, so yes. I changed my mind. It's not psi, it's beta. That's better. That's a better letter. Beta. Of course, thank you. Useful as always. AJ, thank you. No, of course it's beta. Yes, thank you. Okay, so now we're done with that. And now based on this black triangle, so this triangle, this big black triangle, okay, this one. Okay. So I think that you guys can see that our h is equal to maybe differently. Let's do tangent tan of theta is equal to h divided by x1 plus x2. Yes, so our h is equal to exactly 10.062 times tangent of 40 degrees. Grab your calculators and obtain that our h is equal to approximately 10.135 inches. Okay, so we are done with h. And now let's find d. So also based on this black triangle, I'm gonna write here, okay? Here I have some spot. So based on that black triangle, I believe that our cosine theta is equal to x1 plus x2 divided by L1 plus d, right? I believe so. So d is equal to x1 plus x2 divided by cosine theta minus L1. Plug in values. D is equal to 10.062 divided by cosine 40 degrees minus, I believe, 3 inches. So D will be approximately 10 0.135. Inches, of course. Okay. Inches. Okay. Clearly a geometric approach, don't you think? It's clearly a geometric approach. Okay. So we are done with this value as well. So in order to find omega BD, we must also find VB. Anybody want to help me? How to find velocity of this point? Yeah. And we don't need that black triangle anymore. Yeah. How to find velocity of this point? Yeah, Trevor?
Vector analysis of
BNA, exactly, yeah. We can do vector analysis. However, do you remember our discussion on last Wednesday? We covered their rotation about fixed point. And A is fixed point. So we can actually go for the simplified versions of what you said, yeah? So we can actually go for, so VB will be equal to omega AB times L1, yes? L1, this distance. Okay, let's plug in values. So that omega AB is that strange number. I don't remember that number. Wait a second. 209.4395. 209.4395. And L1 was 3 inches. So if you grab your calculators, you will obtain that this value is approximately 6 to 8.3185 inches per second. Okay, and now just plug this value here. Oh, sorry. So now we know that our omega BD is equal to VB divided by D, and this is equal to 6 to 8.3185 divided by D. I forgot how much D was. Let me scroll up the board. D was 10.135. 10.135. Grab your calculators and obtain that our omega BD is equal to approximately 61.995 radians per second. Okay. And now let's finally find VD. So we found this value as well. So now we can find VD is equal to 61995 times H. And how much was H? Oh, wait a second. So I made a mistake, right? Yeah, there's a mistake. So sorry guys, here on your left hand side, D. Oh, that was okay. That's okay. Yeah, but this is not true. This is not true. Sorry, that H is not true. Yes, sorry guys. Okay, so this is correction in your notes. H is equal to actually 8.443. Okay, sorry for that. Yeah, sorry. Yeah. Yeah. So that would be 8.443. Grab your calculators for the final time today and obtain that our VD is approximately 523.424 inches per second. Okay. Before we go, we finished that problem. Yeah? This is the answer. They ask us to find velocity of point D using instantaneous center of rotation. However, on Friday, we solved exactly the same problem differently. Yes, and we obtained on Friday or last time, we obtained that VD was approximately 523.4197 inches per second, What's the source of this discrepancy? Why today we obtain different number? Yes, Ian? I didn't hear what you say. The answer is rounding error. Yeah, so there's rounding error. Okay, thank you for your patience, guys. It's 11:51, so thank you for today and hope to see you on Friday. Bye.